Moon water revolution: how sunlight could power lunar settlements. Scientists have successfully extracted water and oxygen from moon dust using solar energy, offering a potential solution for lunar colonization. This process could enable astronauts to breathe air and fuel rockets. However, its feasibility depends on economic viability and infrastructure development costs. A Chinese-led research team claims they developed a novel method combining lunar regolith as a catalyst to produce methane, which could replace traditional rocket fuel. This approach reduces steps and machinery required for extraction but faces challenges in transporting supplies due to the vast distances between Earth and the Moon. The process relies on lunar regolith, which contains minerals like ilmenite capable of catalyzing reactions. While this method may be efficient, current technology requires additional steps, such as tiling the soil to distribute heat evenly, which increases complexity. Metzger highlights that even simple exhalation of carbon dioxide would only provide a tenth of the required amount, raising questions about whether space-based solutions would truly meet practical needs. Despite these challenges, the research team argues that the technology could be scaled up for long-term lunar operations. The next step is to demonstrate scalability and adaptability to extreme conditions on the Moon. Solar-powered device extracts water, oxygen, and fuel from lunar soil. Imagine being able to turn the Moon's barren surface into a self-sustaining oasis for astronauts, right from the soil beneath their feet. That's exactly what a recent discovery suggests is possible, thanks to a groundbreaking solar-powered device. But here's where it gets truly revolutionary. This device can extract water, oxygen, and even fuel from lunar soil using nothing more than sunlight and the carbon dioxide astronauts exhale. The story begins with samples collected by China's Chang'e 5 mission, which brought lunar regolith back to Earth. Researchers led by Lu Wang at the Chinese University of Hong Kong, along with collaborators, have devised a method that utilizes these samples to create a closed-loop system for resource generation on the Moon. The process works like this: when lunar soil is exposed to sunlight inside a specially designed reactor, it releases water trapped within its mineral composition. This water then interacts with the CO2 exhaled by astronauts, catalyzed by certain minerals in the soil, to produce carbon monoxide, oxygen, and hydrogen. The hydrogen and oxygen can be combined to form water again, ensuring a continuous supply, while the carbon monoxide and hydrogen serve as valuable fuels. But what makes this method particularly exciting is its simplicity and potential for sustainability. Traditionally, extracting resources from lunar soil has been proposed through complex, energy-intensive processes that may not be viable for long-term colonies. Wang's team has shown that a straightforward solar-powered reactor could be the key to overcoming these challenges. One of the key minerals believed to play a crucial role in this process is ilmenite. According to Haihui Joy Jiang from the University of Sydney, this discovery opens up new possibilities for resource generation on the Moon. However, she also points out that there are still important questions to address before this method can be implemented on a larger scale. Scaling up this process to meet the needs of a lunar colony presents several hurdles. The harsh lunar environment, characterized by extreme temperature fluctuations, intense solar radiation, and low gravity, poses unique challenges. Additionally, the variability in lunar soil composition and the limited availability of CO2 could complicate the process. Despite these obstacles, the potential benefits are enormous. A successful deployment of this technology could significantly reduce the logistical challenges of supporting human life on the Moon, making it a more feasible and sustainable endeavor. So, what do you think? Could this simple yet innovative approach transform our understanding of lunar colonization? Or are there unforeseen factors that could complicate its success? Share your thoughts in the comments below. Revolutionary tech, converting moon dust into water and oxygen for lunar bases. Imagine turning the Moon's dusty soil into a steady source of water and oxygen. This breakthrough could revolutionize how we establish and sustain lunar bases. For decades, the biggest obstacle to building long-lasting habitats on the Moon has been the scarcity of water. But a recent study reveals an innovative device that not only extracts water by heating lunar soil but also converts astronauts' exhaled carbon dioxide into breathable oxygen and useful fuel within the very same system. This dual-function approach may be a game-changer for future space missions. Lu Wang from the Chinese University of Hong Kong puts it best: "We never fully appreciated the magic properties hidden within lunar soil." The research team believes their one-step process could dramatically reduce the amount of expensive supplies astronauts must carry all the way from Earth. Here's the thing: transporting water from Earth to the Moon is incredibly costly and impractical. NASA estimates it costs roughly $83,000 per gallon to launch water beyond Earth's gravity. Considering that each astronaut needs about 4 gallons of water daily just for drinking, not counting uses like washing, cooking, or growing plants, the total volume for a 6-month mission quickly becomes enormous. Even with the decline in launch prices over recent years, the weight of water remains a major hurdle, often becoming the single most expensive cargo item. This economic reality is pushing space agencies toward what's called in situ resource utilization, ISRU, the art of making vital materials like water, oxygen, and fuel directly from local lunar resources. In 2020, the Chang'e 5 mission returned samples from the Oceanus Procellarum region on the Moon, revealing that lunar soil contains about 170 parts per million of molecular water locked inside typical minerals. This water mostly forms when solar wind protons collide with oxygen atoms on the surface, producing tiny hydroxyl and water molecules stuck to glassy and silicate particles. Because solar wind affects all sunlit areas, even lunar regions far from the poles, previously thought dry, have measurable water content. But there's a catch: the concentration is low. To collect just 1 bucket of water, miners must process tons of lunar dust, making extraction a daunting task. Yet the potential benefits outweigh these challenges. Water is essential not only for drinking and life support but also as radiation shielding. Moreover, when split into hydrogen and oxygen, it becomes a powerful rocket propellant. The groundbreaking device developed by the researchers uses photothermal catalysis, concentrating sunlight onto a black ceramic reactor until its walls reach scorching temperatures above 1,800 degrees Fahrenheit, nearly 1,000 degrees Celsius. This heat vaporizes the water trapped in the regolith minerals. But here's the clever part: instead of using separate machines, the system simultaneously uses the heat to convert astronauts' exhaled carbon dioxide into oxygen and carbon monoxide, both vital for breathing and fuel production. In practice, samples of Chang'e 5 dust and synthetic lunar soil were packed together around a quartz viewing window, allowing concentrated light to penetrate. The more light intensity applied, the faster the chemical reactions proceeded, proving sunlight alone can power the entire process without relying on electric heaters. The design's simplicity, with no pumps or moving parts touching the soil, helps keep the system compact and robust. Imagine a lunar lander about the size of a household refrigerator capable of processing hundreds of pounds of lunar soil every lunar day, generating water and oxygen for a crew. A material called ilmenite, a black titanium iron oxide abundant in the lunar maria, plays a starring role in this chemistry. Ilmenite not only harbors hydrogen atoms but also contains iron that facilitates the electron transfer needed to convert CO2 effectively. Experiments suggest that 1 ton of ilmenite-rich regolith can produce between 112 to 168 pounds of potable water, more than enough to meet the daily needs of around 50 people. And as a bonus, this process also leaves behind metallic iron, a valuable resource for constructing future lunar habitats, radiation shields, or infrastructure. This could mean that future lunar settlers aren't just extracting water and air, but also producing building materials directly from the dust beneath their feet. However, mining ilmenite isn't straightforward. These mineral-rich deposits are mainly found in basaltic plains, so explorers will need detailed geological maps, and potentially heavy machinery, to pinpoint and prepare optimal sites for reactors. That said, numerous challenges remain before this technology can be routinely deployed. The Moon's extreme temperature swings, from 260 degrees Fahrenheit baking daytime heat to a chilling -280 degrees Fahrenheit at night, can damage equipment seals and warp lenses. Space radiation bombards electronics with charged particles, gradually degrading their components. Lunar dust is notoriously sticky and abrasive, posing risks to joints and filters. Plus, soil composition varies significantly across different craters, meaning reactors must be adaptable to changing materials. The researchers stress that tackling these technical hurdles, along with the significant development, deployment, and operational costs, is crucial to realizing sustainable lunar resource utilization and supporting long-term human exploration. But the momentum is undeniable. China aims to establish a robotic lunar base near the South Pole by 2035, while NASA's Artemis program plans multi-week crewed missions and a permanent orbital gateway. A compact, sunlight-powered system capable of transforming lunar dirt into air and fuel might just be the missing link that turns these ambitious plans into reality. The full study was published in the journal Joule. If you found this fascinating, consider subscribing to our newsletter for more insightful articles, exclusive updates, and compelling stories about space exploration and Earth sciences. Also, explore EarthSnap, a free app brought to life by Eric Rawls and the Earth.com team, offering fresh, engaging content on our planet and beyond. So here's a burning question to leave you with. Given the technical complexities and costs, do you believe in situ water extraction on the Moon is worth pursuing as humanity's next giant leap? Or should we focus on other technologies first? Share your thoughts below, this debate is just getting started.